Hello everyone. I hope everyone's doing fine today. Got a lot of material to cover today, so I'm going to be moving right along. The other day I had a debate with an individual who claims to be a physicist. His name is Peter, and it was on this program. It's JFG's, call him JFG because it's very hard to pronounce his last name, I guess, Gariepy, and known as the Public Space. It's a podcast. He brought physicist Peter, and who debated me on not only physics but in general, but also on the rope model. Okay, so I'm going to be analyzing what we discussed. It took 3 hours. That's how long it lasted. So it was a long debate, and a lot of it probably was unnecessary. We just went into so many details that I think a lot of people were turned off. But at the same time, that's what science is. Sometimes you have to get to the nitty gritty, and that takes time and that takes space. So keep that in mind. Anyways, we had a debate, and these are the problems that I saw with the debate. I'll call it the Peter problems, and I'll call it Peter problems because he asked to remain anonymous. And I'm saying that that's a problem. I'm going to talk about that in a second here. He didn't understand the golden principle of physics, and he said he did, that he agreed with it, but then he never used it. And whenever I confronted him, he rejected it. I'm going to talk a little bit about that, quite a bit, in fact, about that. And I probably won't be able to cover all these subjects today, so I'm going to leave those to next week if necessary. But this is the material I'm going to be covering. He invokes mathematical physics jargon and therefore, a lot of unscientific notions. So we need to know what science is. We need to put this in the context of science and physics. He dismissed strategic words as petty semantics. These are words that made or broke his arguments, and he was not aware of that. And so I'm going to show where he fails on this. This is an important point. A lot of people just want to say, "Oh, Bill, but you're just doing semantics." Well, it's more than semantics. What we have here is a situation where words matter. And he didn't read up on the rope hypothesis. That was quite unfortunate. He also invoked the planetary model of the atom to make his case. It's Bohr's model, the Bohr-Rutherford model, the orbiting bead, and quantum mechanics. They do, they do that quite a bit. They always use the planetary model for almost every explanation, and then what happens is, they they dismiss it. They deny it at the end of the show. They say, oh, by the way, that atom I was talking to you for the last hour, that's not our atom. And they do the same thing to high schoolers. You go to high school, they teach you the planetary model, and you say, well, is that really the super duper, authentic atom? And they'll say, well, no, when you get to college, we'll show you the real one. And so that's somewhat of a problem. And because of that, since you have the orbiting bead, he had to improvise a bogus fabric medium. He called it the rag, or the potential, or whatever. He used all these names to refer to it. And again, it shows that he didn't understand the golden principle of physics, as I said in point number 2 there. And so I dismiss him as a physicist. He's not a physicist. He's an abstracist. He does so-called physics with abstractions. If you're going to do abstractions, you're an abstracist, not a physicist. Physics is the opposite of abstract. Anyways, these are the problems I'm going to be dealing with. Let's start with the first one, anonymity. Peter decided to remain anonymous. He did not furnish his last name. live. He asked to be presented as an experimental and phenomenological physicist. Okay, and again, I'm saying that's an abstracist, not a physicist, because what he does, what phenomenology does, is the application of theoretical physics to experimental data by making quantitative predictions. So if he's going to be doing predictions and he's going to be doing quantitative, he's an abstracist. He's not a physicist. And predictions already take them outside of science, let alone out of physics. We don't do predictions in science. Maybe he's not an abstracist. Maybe he should be regarded as an astrologer or a palm reader. Those people do predictions. And you might say, well, Bill, what are you saying here? You're saying that, that in physics and in science, we don't do predictions? This notion that science is associated with predictions or that predictions are associated with science, that's been around for decades now. Karl Popper talked about them, in the 30s and 40s. So it's like it's common knowledge that predictions are part of science, and people get are horrified when I tell them predictions have nothing to do with science. So let's put predictions in the right context so that we understand what the mathematicians mean by predictions and why it's not a part of science, not the word prediction, at least. Here's a prediction for you. Here's a paper that these guys have. And this paper says predictions from an anisotropic inflationary era. What are they talking about? Inflation is Alan Guth's, I guess, I don't know how you pronounce his name exactly. Inflation is what happened after the first few microseconds or seconds after the Big Bang, 14 billion years ago. There was a rapid process, okay, and they call that rapid process inflationary theory. Anyways, now it's part of standard cosmology. All these astronomers, they believe in this inflation theory. And here these people talk about making predictions of an inflationary phase. And you say, hold it, what do you mean prediction? You're predicting what happened 14 billion years ago? What do you mean by this? What do you mean you're predicting? Are you predicting the past? Is that what you're doing? And so there's something seems incongruous here. They're talking about what happened 14 billion years ago, and they're using the word prediction. And you're saying, what can that possibly mean in that context? What could the word prediction mean in the context of 14 billion years ago? Usually we predict the future, not the past. Imagine you go to the astrologer, and he said, I'm going to make a prediction. I said, okay, make a prediction. He says, I'm going to predict when you were born. Huh? What do you mean? And through some kind of trick, he found out my birthday. He says, I predict you were born on November 19th, 1952. Well, he said, it's correct, but is that a prediction? So something is wrong here. Something is incongruous. How can you predict what happened 14 billion years ago? And this is the context. The context is these people are not predicting. What they're doing is explaining, but they never realize that, they're explaining. They call that a prediction. They're making a model. They're making a model of what the initial conditions could have been or should have been 14 billion years ago in order to arrive at where we are today. It's kind of like this. Let me give you an example. 14 billion years ago, you say there were caterpillars. That's why we have butterflies today. It's more or less like that. So if we verify that we have butterflies today, we say, that confirms my theory that the initial conditions were, caterpillars. It's more or less like that. But what they're doing is explaining why there are butterflies today. It's not a prediction. It's like when I do predictions all the time. My famous prediction is the extinction. mass extinctions. What do I say? How do I phrase it? I say, well, imagine you were at the starting line of the Cambrian 542 million years ago, okay? So now if you're standing there, you can predict, quotations here, okay? You can predict, and I'm trying to explain extinction, right? Past extinction, but I'm saying, what if you were standing at the Cambrian line? You can predict that certain plants are going to periodically disappear. So the ferns disappeared, they were replaced by conifers. Conifers disappeared, they were replaced by angiosperms, flowering plants. And when that transition happened, at some point there, that's when all the animals became extinct of that era. Why? Because all these animals, these dynasties of animals, forged a relationship with those plants for millions of years. They can't change their diet at the last moment. And so when the plants disappeared, they disappeared, and the new plants came out. So is that a prediction? No, I'm trying to explain extinction. I'm trying to explain extinction based on the fact that, plants have been replaced periodically over time. So they call that a prediction. It's not a prediction. I'm trying to explain a mechanism, how Mother Nature does mass extinctions. Well, it's similar to this. What they do is they go back in time. They say, if these were the initial conditions right after the Big Bang, we should expect this to be observed today. It's not a prediction. They're trying to explain why we ended up the way we ended up. That's what they're doing. They call these explanations, they call them predictions. They're simply running a thought experiment in which a movie they want you to watch, and they say the reason we have galaxies and stars and gases and matter and it's the way we have today, it's because this should have happened sometime in the past. That's what they're doing. It's not a prediction. So no, we don't do predictions any more than, whether, and it's interesting. I looked up deductive and inductive predictions, and they don't use essentially the word prediction. What they say, they use the word explanation. You can look it up yourself. You'll see that the so-called prediction is really an explanation. They're trying to explain something. And so they go through this inductive and deductive reasoning, deductive being, when you can guarantee the result, that's math. And then they have the inductive one where it's usually qualitative explanations. And they're trying to explain something. They're trying to explain some result, and they say, if A and B, then C. That's not a prediction. It's not a prediction. What that is an explanation in one case, a description in another. That's all it is. So no, there are no predictions. We don't do predictions in science unless you can justify what a prediction is. Prediction is what astrologers do, and they want to dismiss that as, oh no, those are prophecies. Well, yeah, there is no difference between a prophecy and a prediction. The only predictions there that you can say relate to science, and they're really not, is like when you do an experiment. You can tell me the exact result of an experiment. Then you could talk about doing predictions. And since nobody can do that, there are no predictions. All we have is intelligent guesses. And I always give that example of the guy who lets go of his pen 100 times and says, I can predict the pen is going to fall to the floor. Unambiguously. I said, okay. So he does it 100 times. And I say, okay, I'll bet you a beer that now it won't fall to the floor, because usually it happens on the 101st time that you do it. He says, you're crazy. Oh, well, let's try it. Okay, so he lets go of the pen, and this time it doesn't fall to the floor, it stays in the air. How did that happen? See, you didn't predict. It stayed in the air. It turns out I have a couple magnets that are holding the thing up in the air. So he's counting on gravity. He wasn't aware that I had these two magnets, so he didn't predict. He was guessing. He had an intelligent guess that based on his experience, it was going to fall to the floor, but he wasn't aware that I had two magnets. I cheated, yes, but I won the beer. Okay, there is no such thing as prediction in science. We do not predict. What we do is explain. So if Peter, what he does is do predictions, then he's already on the wrong foot. And by the way, I do want to commend him. On the other hand, it's not all negative I got to say about him. I think he's a pretty intelligent guy. You know, unfortunately, he's using his intelligence to do quantum mechanics. And the only thing I can recommend to him is that, you know, he get out of the particle model, because he's not going to answer any questions with particles. But on the other hand, he is, I think, a serious researcher, and that is commendable. I have a lot of respect for that. Okay, so I want to put that on the line as well. Anyways, what are the problems with what what Peter was saying? Well, the first one was, you know, that he didn't give his name, and I think that has a lot to do with the environment that we have today in science, that people are scared to really go out on the limb. And that's unfortunate in his case. He's a young guy, he's trying to make his way in, you know, his career, etc. And if he has different ideas, or, you know, he wants to explore different alternatives, he should not be censored because of this. And the only reason I can think of that he wanted to remain anonymous is the environment that we have in science, in so-called science today. And that is that we have witch hunts. And people are worried about losing their jobs or their careers because they went out there and they said something, and their colleagues look at them and say, well, what did you say? What did you say about quantum? What did you say about general relativity? And so they're scared. And so they'd rather not, you know, give their names out, or be too popular when they're raising issues that can be considered or regarded as being crank or crackpot theories or whatever. So that's, I think, the worry. Otherwise, I don't know why he would want to remain anonymous. And I'm going to honor that, by the way. I'm going to keep him anonymous. He can come out of the closet on his own. You know, I'm not going to out him using this in scientific context. Okay. The first issue I had. Let me put that up there one more time. Where is it? The problems. Anonymity. The second one, he didn't understand the golden principle of physics. Let's look at that one. Here's the golden principle. I said I hinted to him that, you know, the golden principle of physics is that physics requires an object. You can't do physics without an object. And Peter says, probably you're right. And then shortly after that, he said, you do need an object. Well, he said all this, but he doesn't understand the contract that he signed here. You know, how can you say that you need an object and then the rest of your presentation you do concepts? And again, every word in the dictionary can be divided into two categories: objects and concept. There is no third category. If you do, you have to tell me in what way it's different than a concept or an object. So what is an object? It's that which has shape. That's what it is. And a concept is a word that invokes or embodies two objects. You need to define the word object before you define the word concept. Object is to one what concept is to two. Okay, that's the beginning. That's the starting point. Okay, and but we never got to a real definition of object. But I'll get to that in a second. So where's the problem? The problem is that Peter sends me 4 papers. This was ahead of the debate. Okay, sent me 4 papers, and I read those papers. And it turns out that they contain no objects whatsoever. They're all concepts. And for a guy who says that he agrees that there has to be an object, that's kind of weird. We got a problem. We got to resolve that. There's a problem there. Okay. So here are the 4 papers that he sends me. He sends me the following papers, and I look at them, and then not one of them contains a picture or a drawing of an object. They're all concepts. And JFG last time, not this time around, but the previous time when he interviewed me online, he came up with the idea that, well, concepts always implicitly have an object underlying them. That was what he was saying. Yeah, but in physics, you have to identify that object. You can't just talk about fields, energy, force, mass, whatever, and not talk about the elephant that's underneath all that, or whatever object that you're going to use. So the object must be identified, and we don't have that in all of mathematical physics. In other words, if you look at all the invisible mediators, like for light, for gravity, for magnetism, etc., we don't have, the mathematical physics does not provide the invisible mediators. Okay, and that's the problem today. The problem is that we don't have physical mediators. And okay, let's look at that first paper. The first paper is Tanimura's paper. Okay, it's experimental confirmation of the Aharonov-Bohm effect. Okay, so what do they talk about? Well, in this paper they talk about the existence of an effect. That first line already is unscientific. Why? Because effect is a concept. It's not a physical object. And this is not semantics, fellows. Okay? This is that you can only talk about the existence of objects in physics and in science. It is in ordinary speech where we can talk about the existence of concepts. For the purposes of physics, you can't say that love exists. You can't say that intelligence exists. You can't say information exists. And of course, you cannot say that an effect exists. And so that first line already makes it unscientific. It would have been rejected, never been published in a scientific magazine. But in mathematics, everything is possible. They publish this stuff. And further down below, you'll see, again, demonstrated the existence of the AB effect. Again, existence of an effect. So they're kind of trying to prove, they talk about demonstrating, meaning they're proving, okay, the existence of an effect. And so we gotta stop there. We gotta analyze what this is all about, because this is not semantics. This is getting to the heart of what the problem is. The word exist belongs exclusively to physics. It doesn't belong to religion. Anyone using the word exist has crossed the line into physics. Why? Because physics is the science of existence. Physics only studies that which exists. We have to define the word exist, and it's never been defined. I'm the first person who defines it. I'm not claiming, I'm not boasting here, I'm just saying a fact. The fact is that no one has ever defined the word exist. In fact, if you go to the Stanford Encyclopedia of Philosophy, they go, the fellow who defines the word exist goes through this whole analysis, 2-hour analysis, and in the end he said, well, we still haven't reached a decision. So he doesn't know what exist means. You look it up in the Wikipedia, again, you don't have any idea what exist means. There's all these if, ands, and buts. And funny thing is that when you go to the Catholic Encyclopedia, you will not even find a definition of the word exist. There's no analysis whatsoever, nothing written about it. And yeah, exist for the purposes of science means physical presence. Physical involves an object. You must have an object to talk about exist. Concepts cannot exist, not in science. In ordinary speech, yes, not in science. If God wants to exist, he's got to also have location. Not only does he have to be an object, a human being, a flaming bush, whatever, he's got to have location. God cannot be grace and pretend to exist. You do not pray to grace. You pray to a man, a bearded guy out there who's going to concede, a favor to you. But you cannot pray to a concept. You cannot pray to love. Okay, love doesn't have ears to hear you. So for existence to work, for that word to be used consistently, scientifically, rationally, you must have a physical object. And that's not enough. It has to have location. There's got to be a distance between God's chest and my chest, or between God's body and a chair and a tree. Okay? So exist is important because the word exist is important, just like the word object is important in physics, because physics is the science of existence. Physics only studies objects that exist. Physics only studies that which exists, and anything that does not exist, physics is not interested in it. Okay, so continuing with Tanimura here real quick. You can see down there at the bottom, it says, even when the magnetic field was confined. A field confined? How do you confine a field? The field is a concept. And again, these are not semantic arguments. These are things, these are words that these people use as physical objects. They're treating field, which is a concept, they're treating it as a physical object. So we do have to get to the bottom of what a field is before we can talk about its existence or confining it, doing anything with it. Can you do anything with a field? And for that, we go to the word field. Let me get it up here. And these are fields. What is a field? Well, in the religion of mathematics, a field is a quantity. This is out of Wikipedia, okay? But you can look it up anywhere else. You'll find more or less the same notion. That has a value for each point in space and time. Field is essentially quantities in a region. That's what a field means, region of values. That's what it is. And there you have a few regions of values. The first line up there with objects, the bottom, the one below the line are without objects. And so if we're gonna, like mathematical physics does all the time, they dispense with objects, then at the bottom you have it without the objects. You have fields that have no objects in them. That's the raw field, you could say. That's what a field is. And what are we staring at? Well, we're staring at vectors. Each one of those arrows are not Indian arrows. They are vectors. What is a vector? It's a line, a mathematical concept that has only magnitude and direction. So it's a value. It's a quantity. That's all it is. That's what those arrows are. So what is a field? It's a bunch of vectors, a bunch of quantities and directions. That's it. And what is a particle? They say, well, it's a field. It's a vibrating field. They're saying that these vectors, these lines are vibrating. And what are the lines? They were magnitudes. They're numbers. So the number 5 is vibrating. That's essentially what they're telling you. This is not semantics, folks. This goes to the heart of what these people are saying. They're saying that a particle is a vibration of a field. And so what is a field? A field is a bunch of numbers. And they're saying the numbers are vibrating, and that's what creates a particle. That's what these people are saying. So yes, it's important to analyze the word field, and no, this is not semantics. This has to do with the foundations, what this guy has in his theory. He's saying a particle, he's presenting a particle, and he says it's a vibration of a field. First, vibration is a verb. So if a particle is a vibration, he's automatically turned a noun into a verb, or the opposite. He turned a verb into a noun. That's the first one. The second one is the vibration of what? Of a concept, of a number, of a value, of a quantity. So this is the issue. The issue is there is no physical object called field, and these people are treating the word field as an object. This is the problem. You have quantum field theory and so on today. That's replaced a particle. So Tanimura already has a bunch of problems with his paper, and this is just the abstract, by the way. So we have a problem with existence of effects, of concepts. We have a problem with a field, but then we have a bigger problem here also. It says measured between two electron waves passing through spaces inside and outside a tiny ferromagnet. Electron waves? What are they saying here? How can we have electron waves when the same Tanimura wrote a paper which I analyzed in my video, the one about the Slit experiment? You can look that up in my site. You'll find the Slit experiment in there. I talk about Tanimura's paper, and here it is. This is his paper, the one at the bottom. We have Mr. Merli, an Italian group that handled one electron at a time, or so they claimed. Tanimura handled single electron buildup of an interference pattern. So he says he handled single electrons. So he's treating the electron here in this paper, he dealt with it as a particle. Now, in his new paper, he treats it as what? Treats it as a wave. He said electron waves passing through spaces. So we got a little bit of a problem here because, these people use the wave when it's to their advantage. and then they treat it as a particle in another context. You see what's happening here? You know, we have here the electron waves, and here in this one he talks about single electrons. In other words, treating it as a particle. It is this thing, the fact that they sometimes talk about particles and sometimes about waves, that allows them to cover all the bases. Wave is a concept. Particle, if we're talking about a corpuscle, because that's essentially what he's referring to when he says single electron. He's saying a ball hit the wall, right? You know, that's an object. So the electron is both a concept and an object. And that's what allows them to get around, you know, any criticism of their physical interpretations. The fact that they're treating God as both a concept as an object. God is this human-like magician that made the universe, right? And God is also maybe a flaming bush. That's on one hand, that's the object. And then as a concept, you know, you go to the New Testament, you listen to John, and he says, you know, by the way, you know, God is love. God is spirit. So what is God? Is God an object, or is God a concept? And we have the same problem with the electron. The electron, according to Tanamura, passes through the slit, you know, through the space in the slit, passes as a wave. And then he detects it at the screen as a hole, as a particle, as a, you know, the cannonball hit the wall and made a hole. And so, you know, what is the electron? And for this, we don't have to talk about his conclusions. What we have to do is say, look, Tanamura, begin by drawing your atom. Let's look at your atom. Let's see what you're talking about before we can get into your theory. And that's the problem we had also with Peter. He didn't understand that. He thought that was nitpicking or doing semantics. No, we need to know what your atom looks like before you start your theory. Otherwise, we're not going to listen to your theory. It's worthless. You could be talking about spirits and angels for all we care. You need to draw the atom. You need to tell us what your atom looks like. And specifically, you know, if we have the electron bead going around the atom, if that's going to be the bead that's going to hit the wall, the electron bead, if that's going to hit the wall because you pulled it out of the atom, because that's going to be your theory, then we need to know, you know, why that electron bead sticks to the atom to begin with. Why doesn't it fly away normally? Why do we need to heat up, for example, the atom to ionize it? Why isn't it ionized spontaneously at every moment? Why doesn't the atom disintegrate? And that's when he came up with a rag. I'll get into that in a minute. But you can see the problems with Tanamura. Tanamura first talks about existence of concepts. Let me put that up there again. He talks about existence of effects. He talks about fields, confining fields, and he talks about electron waves when what he's detecting are particles. So, you know, his whole report here is worthless. It has nothing to do with science. Okay, so it's important to trash whatever his group did, because all they're doing is just doing a bunch of verbiage, and it doesn't conduce to anything. We are not understanding what these guys are doing. They think they detected single electron hits on the wall, and you know, when you know, there is no evidence of that. Their language completely is bogus anyways. None of it passes the minimum criteria of science. So Tanamura's reports are worthless. It has no place in science. That's Tanamura. What was the next paper? The next paper was a superposition paper for the 3-slit experiment. Now we don't have 2 slits or 1 slit. Now we have 3 slits, okay? And here it is. This is what it looks like. Here's the paper. A little more. Okay, exotic looped trajectories of photons in 3-slit interference. Well, again, we're going to have the same similar problem because they're talking about trajectories of photons. They're assuming a photon is a discrete particle. They treat it as such whenever it's convenient to them, and when it's not convenient to them, they bring in the wave, and they say, well, it's an elongated wave made of many links, many wavelengths. Okay. Okay, the first problem I found is that, they say tenets. They say the validity of the superposition principle and of Bohr's rule are well accepted tenets of quantum. Well, the word is tenets, and that already gave me an idea that not only the authors of this report, but the peer reviewers were not paying too much attention, because that caught my attention immediately. And so that's the first, just a minor thing there, but just keep that in mind for when you see these papers that are said to be peer reviewed by the highest peer reviewers on earth. Well, not so. If everybody missed that, and that's the first line, and it wasn't correct, that means you wonder about both the authors and the peer reviewers. So where's the problem? Well, again, they talk about predictions, and here they're talking about well accepted tenets of quantum mechanics. Well accepted by whom? Was it by mathematicians? Well accepted is like saying, we proved it, so you better swallow it. Okay? Because we already proved it. It's well accepted. Okay, so what do they talk about here? They talk about superposition principle. What the hell is a superposition principle? Well, I dealt with that a couple weeks ago. More like a month, I guess. Let's look at let's rehash our superposition nonsense here. First of all, here we have this is the other side of that report. The first one was the official report. This is what they published in Quantum Optics, and again they say it's and this is the context. They're saying first they put a prize, okay, for he who could disprove the principle of superposition, and with it they would disprove quantum mechanics. And so first they offer a prize, and second, which is very unscientific, science is not a beauty contest where you get medals and prizes, okay? And second, they talk about disproving. Okay, again, has nothing to do with science. Disprove means that you do not believe. That's what it means. They've already proven God to some people. They disproved it to other people, so who's right? Well, it depends on your personal beliefs. So disproving and proving have nothing to do with physics. And again, to investigate whether superposition really occurs in nature. So they're talking about just verifying whether something occurs in nature, and whether something occurs in nature, and that's not science. Science is about explaining why or the cause of something, not to say that it does occur. If I throw a stone through the window and break it, and they say, well, why don't you repeat my experiment to see if it's true? And so now I throw a stone through a window and say, yeah, it's true. Every time I throw a stone through a window, it breaks it. Is that science? Or is science understanding how the window broke, explaining how the window broke? But to repeat an experiment like, throwing the pen, letting go of the pen, letting it fall to the floor constantly, say, well, yeah, pen always falls to the floor. Is that science? Is that physics? That's the point. The point is that we need to understand what causes the pen to fall to the floor, not to run an experiment a million times and say, yeah, the pen always falls to the floor. I did the experiment repeatedly, so I'm doing science because of that. Okay, so superposition. What did we cover a couple weeks ago or a month ago or whatever? Here's superposition and decoherence. You got both of them here pretty much. Superposition means you can have two states of a particle at the same location. And then the other one is that you can have the particle at two places at once. That's decoherence. Okay, so we have the superposition and decoherence right there, and this is not mine, by the way. This is from the official people of, this is the party line, from quantum physics. And if you still didn't understand, well, maybe you can get a better glimpse here where we have, what's his name, Dr. Quantum. And he does decoherence with particles as always, you know. So let's start at the beginning. Let's wait here for a second until it starts at the beginning. You'll see in a minute how Dr. Quantum cries. I like that. I put that in there, you know. You'll see it here in a second. He's crying because he can't figure out how this universe works. That's why he's crying, okay? Anyways, he starts out with a marble machine. So he's going to do it with particles. And with particles, he gets one slit and he gets just one line. Puts two slits, you're supposed to get two lines, but he always does it with particles, and now he gets, you know, the fringes. Okay, that's the slit experiment. Then he tries one bullet at a time. And since he can't explain why it also produces fringes, what he does, that's the explanation he does, he says, well, what we have is that the particle is at two places at once. And then when it goes to the blackboard there, or the screen, whatever is behind that, then he says, well, the particles now, you know, are both at the same place at the same time. So what they're doing is cheating. They're saying, you know, since we cannot explain this rationally, what we do is we say that the particle is at two places at once when it hits the two slits. There's only one particle, but it's at two places at once. And then when it goes to the screen or to the blackboard there, what happens is the single particle comes back together and forms a single whole, you know, on the blackboard. And yeah, no, that's why he cries, because that's the best he can do to explain, you know, the slit experiment. And this is cheating. This is cheating first because, you know, first they play around between particles and waves, you know, and I always like an analogy for that, you know. I said, did you see the leprechaun? Yeah, I saw him, and I tried to grab him to steal his gold. And what happened? Well, he turned into a spirit, so I couldn't grab him. You know, I mean, anyone can explain physics like that if you can convert the particle into a wave and a wave into a particle at your convenience. That's ad hoc. And that's not very scientific. A little more scientific is maybe Karl Popper's suggestion, even though I don't agree with it, but that's beside the point, because the mathematicians agree with Karl Popper. And Karl Popper says, look, if an experiment falsifies your theory, you have to reject the theory. All experiments, 150% of all experiments ever done, debunk, falsify quantum mechanics. They falsify that light cannot, or the electron, cannot be a particle, a discrete particle. Not one experiment can be explained with a particle model. Not one. Look at what I'm saying. And so hold it. How about the Compton effect, for example? In fact, I'm going to be dealing with that in a second. Compton effect is a particle, you know, shows the particle nature of light. No, it doesn't, because if you read Compton's paper, it talks about wavelength. So what wavelength does a particle have? And that's when they have to go to this duality where, you know, you have the little wave, but it's a wave packet. It's kind of chopped off at the edges. And which comes to the question, you know, where does a wave begin? Where does a wave end? I mean, it's easy to say that, but what are we talking about? What is this wave? Wave of what? And they never go through all that stuff. They say, oh, that's semantics, that's philosophy, that's metaphysics. So they dismiss all that and say, let's do the math. The issue is that, you know, you cannot explain even the Compton effect, or the photoelectric effect for that matter, because they all involve wavelengths. Slit experiment, wavelength. I mean, that's how Thomas Young did it in 1800. He became famous because he presented the slit experiment in terms of wavelength. And all of these are done in terms of waves and wavelengths. And particle is incompatible with wave and with wavelength. So that's not when they use the quantum. I mean, if you look at the standard model, there's no such thing as a wave. All you see is these particles, not one of which has a picture in them. That means that they don't know what they look like. They've never observed a particle, as they always claim. Oh, we observed. No, they didn't observe anything. They're blind. You can't see an invisible entity by definition of the word invisible. So you can't see a photon. You can't see an electron if that's what they think they accelerated. You got the Swedish group that says they filmed an electron. What do they film? They don't even know what they filmed. Anyways, the point here is the following, that you need an object. You need a physical object before you can do physics. You have to identify the invisible object, the one that's doing the phenomenon, the thing that you're looking at. And they can't do that. That's why we don't have a picture of a single particle in the standard model. Okay? And so, yeah, that's the problem that with decoherence and with superposition. These people are talking about, let's see if I can get this back up here. Where is it? Slit, here it is. So they talk about superposition principle, but what they're saying is that they believe that they're dealing with particles, with discrete particles. That's the first one. And you can see that in the rest of what's underlined there. Observed such paths. The paths of what? Of a particle. Okay? And they talk about experimental observation. What do you mean observation? Did you observe the particle? No, they did not observe the particle. Like Tanamura, they observed the effects of something that was visible. They observed a concept. They watched a movie of something that they could not identify. They saw the curtain move, and they assumed that it was a spirit. That's what they're saying here. And this spirit in quantum mechanics is known as a particle when it's convenient to talk about a particle, and a wave when it's convenient to talk about a wave. And here they're talking essentially about photons, about particles, about trajectories of particles, because they can't really talk about a trajectory of a wave. Even though quantum says very clearly, and this is, you'll see several authors on this out there, that light travels as a wave and departs and arrives as a particle. So they cannot talk about the trajectories of particles because quantum says that light can only travel as a wave. So what do? They say, well, yeah, it's a wave packet. We have a wave that's traveling, but the wave is chopped off at one end and at the other, and it's a little packet of a ball of energy. So they have the particle mixed with the wave at all times. They need the wave because they need to talk about wavelength and about frequency, and then they need the particle for the impact. And so in between, emission and arrival, what happens to that particle? What is it? And they say, well, it's both. It's a wave and it's a packet. It's a packet of energy, whatever that means to you. It's a vibrating whatever. And unless they tell us what is vibrating, unless they tell us what it is, are we talking about a little ball, or are we talking about a little spring? What are we talking about? And they never will be able to tell you that, because in order to tell you that, they have to make an assumption. They will never be able to see it, and they will never be able to determine that indirectly. All they can do is do some armchair physics, sit back and say, what could it possibly look like that could be doing all these things? That's the only way to come up with, what physical object mediates light, the atom, etc., gravity, and magnetism. Okay, so what do they say? They say they have excitations of surface plasmons. What the hell is a plasmon? So you look it up, and it says in the religion of quantum mechanics, a plasmon is a quantity, an amount of plasma oscillation. It's an amount of oscillation. Just as light and optical oscillation consists of photons, the plasma oscillation consists of plasmons. What is a plasma oscillation? It's a rapid oscillation of the electron density. We have oscillations of density. Does any of that make any sense? They have oscillations of concepts. This is not semantics, folks. This is what they're going to be telling you is a particle. They're treating these things as things, these words as things, and they're not things. A thing is that which has shape. You should be able to draw it. You should be able to illustrate it for someone, so someone looks at it and says, oh, okay, I see what you're talking about. We can't have that in quantum mechanics because they can't tell you what they're talking about. And they confess, here they say, what is a plasma? Plasma is an oscillation. And what is oscillating is a density. So you figure it out. So none of these reports that I was sent are scientific. They have nothing to do with science, let alone with physics. That's the bottom line on all these. Okay, the third or fourth, I don't know where I'm at now, but not important, was this Compton scattering. Again, we get Mr. Compton, we resuscitated him, and he talks about single particle excitations. Again, he's already determined, whoever did this report, they determined that we're talking about particles, and they're single, lonely, discrete particles, and these particles are being excited. And so they've already have this a priori notion of what they're going to be doing. They've never seen a particle, but they're already assuming that it's a particle. Where did they get this? Where did they get the idea that it is a particle? This is an assumption, and their assumption is wrong. There is no such thing as a particle out there. And again, you can see it everywhere in the report. It says multiphoton. Again, you get the word field out there. What is a field? Well, if you look it up, you'll find that it's a vibration of an excitation or vibration of a particle is a vibration of the field. That's what it is. So they go with this, this circular reasoning where we always end up with concepts. You never end up with an object. You never end up with a stone in quantum mechanics. Again, they talk about observation. They observe fundamental linear X-ray matter interaction. They're observing interactions. So what did they see? I mean, you can say you saw a tree. You can say you saw a dog. You can't say that you saw running. And here they're saying they saw interaction. They saw running. They didn't see the dog. Okay? Again, they're talking about two identical photons producing a single photon. And that's, again, this notion that they have that of superposition, and maybe if you run that in backwards, you'll get also decoherence, where a single photon somehow turns into two photons. Momentarily, virtual photons, they deal with all these abstractions to try to give a physical interpretation to what they're seeing in the lab. They never saw anything. All these are assumptions, and they're irrational assumptions. Because for a particle to be at two places at once already has to tell you that you got to reject your assumption and not, force your theory. And again, we measure scattered photons with an energy of blah, blah, blah. Okay, so again, they use the word energy, a word that has never been defined. Richard Feynman says we don't know what energy is, and of course they'll never know. They'll never even bother to define these terms. They don't care. They don't care about language. That's semantics as far as they're concerned. So they dismiss all these things as, petty arguments. They just want to do some lab work, put an equation, and get a Nobel. That's it. That's all they call that science. Okay, so as you can see, none of these reports are scientific. That's why they're not even worth even the time I'm spending analyzing them. But just so that you know what's going on here. And talking about here we talk about knowledge. This same report, if you look it up, you'll find this on the internet. Okay, let me make this bigger so I can read this. My age, you need to make things a little bigger. What did we do, it says. And again, they're talking about this X-ray Compton scattering. And they said the most fundamental interaction, that's what they're investigating, right? Interactions between rays. Rays? Rays is a concept. There is no physical object called a ray. There's no physical object called a beam. Beam and rays are figures of speech. What they're saying is that they have a flow of photons, and they're going to call that flow, that whole thing, they turn the row of apples, they turn it into a line. That's what they're doing here. And they call that line a ray, or they call it a beam. And so now they forget about the fact that they're dealing with discrete photons, and they say, now we're going to talk about interaction between rays. And that shorthand is unfortunate because all that does is show that, that they have no idea of the physical interpretation. What did they observe? They observed a process. Great. They observed a concept. So they didn't see the individual particles. What they saw is a process. What did they see? They say two photons converted into a single X-ray photon. So we have two photons again converted into a photon. And I like that on the next line. It says, we know from experiments. We know. We know means they already decided their dogma. They've got their religion down pat. They're not going to accept any other alternative because they already know. And here I have a comment from Sabine Hossenfelder, a lady who apparently styles herself as a physicist. She's just a mathematical physicist. And in a report little article she wrote, what is a scientific prediction? She says, we know. We know that our present theories are correct to a high precision, and new theories cannot differ by much, or they are false already. So in other words, you better fall in line with quantum and general relativity, because if you depart too far away from those two established, theories, as they call them, then we know that you're already false. That your theory, that your proposal is false. We're not even going to listen to you. You're a crackpot. But what is the issue? The issue is that precision has nothing to do with science. She's talking mathematics. And a theory is an explanation. So if quantum mechanics talks about vibrating fields, which are numbers, vibrating numbers, and a vibrating number is a particle, and general relativity talks about warping of space-time, a concept, and that's what Einstein says is gravity, then we got a problem, because it's got nothing to do with precision. It's got to do with the irrational explanation these people are offering for common phenomena, such as gravity, or for what they call, for light, magnetism, for all these other, phenomena that we see out there. So, that report is unscientific as well. And here we have the fourth one. It's the electropositron annihilation experiments, okay, from LEP. Here you'll see it. Review of final LEP results, okay? And what they do in this report, this is just a simple report putting up to date on, the measurements that they took with this machine, okay? And what are they saying? They're saying the most important improvements being, and they go into vertex measurements. They talk about measurements. So you measure a chair, and that's science. You put your ruler to the chair and you say, well, it measures 2 feet by 2 feet. The seat does, and the legs are, 2 feet also, 2 feet long. So you measured the chair. Is that science? Is that what we'll call science? Or you can do it with weight. You can say, look, I weighed the elephant. Is that science? He measures, 2 tons. Great. Or you say, look, I clocked the lion. He runs at 30 miles per hour. Great. Is that science? Just taking measurements? So keep that in mind. This is what these people do. And they put equations, and they get a Nobel, and they say, oh, see, I did science. And so they're talking about the most important results from the LEP. And again, it's all about measurements. Okay. But they do talk about, positron electron annihilation. You get a positron and you hit it, which is a positive electron, you can say, and you smash it against a negative electron, and you get empty space, I guess. Annihilation kind of says you get nothing. So you get 2 somethings. You get a black ball and a white ball, and it turns into a no ball. Okay, that's what they're suggesting. So where do you get this nonsense called a positron? Well, we got that from Mr. Anderson, Carl Anderson. He got a Nobel Prize for discovering what I call the suppositron. Now, it's suppositron not because it's a suppository, okay? It's a suppositron because he assumed that he was dealing with a particle. And here it is, okay? Here's the suppositron, Carl Anderson suppositron. What is it? What he did in 1932, he took a picture in his chamber, and he found that there's this line, this curve, and it comes from the bottom going upwards, okay? And electrons go from top to bottom, and so he said, well, if this one went from bottom to top, then this is the opposite of an electron. It's a positive electron. And so he came up with the positron. I'm not sure if he was the guy who named it, but the point is, since then it has been called a positron. Positron is supposed to be a positive electron, if you can think of that. And so we have the positive electron, the negative electron, and when you combine, when they touch each other, they turn into nothing. Okay? And so he got a Nobel for this, for discovering this thing. And what are the problems with it? Well, the suppositron, again, is a superposition. Why is it? Well, you see the blow up there, and you can see that there are some little, it's not a continuous line, like there are gaps between it. So the question is, did the suppositron jump like a jumping bean as shown on the right? Did it make a hole and then jump up and then make another hole and jump up and make another hole? Is that how this line was made? And you can see that I put a little drill bit next to it. And you say, why the hell did Bill put a drill bit? Well, because the pattern there looks more like a drill bit. See, it never occurred to Anderson or to any of the quantum people that they're not staring at particles, that they could be staring at something else. And here it is. In the 19th century, which is what these people are doing still, the quantum mechanics, the way they do it is they do their holes, like that one there, like this line. When they want to make a hole in the wall, they bring a cannon, like Dr. Quantum did a minute ago, when he shoots these particles, these balls with his pop gun, and this is how they did it in the 19th century. See, you want to make a hole, you bring your cannon, and you make holes in the wall by throwing balls at it, okay? Wham! That's how they do it in the 19th century. And this is what Carl Anderson thought was happening, that a ball was making holes in his wall. Okay, it was, or maybe a ditch. If it came from the bottom, it was making the scratch, right? A ditch, a channel. And it never occurred to these people that there could be a different mechanism. And here's the different mechanism. There's the one suggested by the rope model. It's a drill bit. We do this in the 21st century. We're a little, we don't bring a cannon to make a little hole in the wall. We bring a drill bit and make it turn with a drill. So quantum is still in the 19th century, making holes in the wall with cannons and cannonballs. And in science, we do it with drill bits. It's a much more elegant, simpler mechanism to make holes in the wall. So compare, quantum's cannonballs, right, to Bill's drill bit. So there's different ways of making holes in the wall, different mechanisms. And I'm saying that electricity, because this is the way they try to explain electricity. They think it's a flow of electron beads. And electricity, I say, is a twirling bit. You have to have all these atoms, and they're connected to each other, physically connected to each other, forming a long string of atoms. And they twirl like a snake, twirling in situ, in place, okay? So I have a different mechanism for what electricity is. And those holes that Tanimura thinks he made by throwing rocks at the wall, cannonballs, bowling balls, we do it a little differently. We do it with a drill bit. We go and make the hole in a different way. And it's got to do a little bit with, that's why I'm saying we should put the slit experiment under vacuum. Let's get rid of all the noise. Let's see if you can produce an electricity in there with nothing in there. If you can produce a total vacuum, if you could remove every particle from your chamber, assuming 10 to the minus 100 torr, be beautiful, because that would eliminate all the noise. Can you have a current? This is the important question. Why? Because, see, these people think they're shooting bullets. And if you evacuate the chamber of matter, you've increased the mean free path. So now your current should flow easier. And that's not the case. It's exactly the opposite. The more matter you remove from the system, the less flow of electron beads that you have. In fact, you won't, if you remove all matter, you won't have any current whatsoever. Because, since we're out of time, I'm going to continue next week. I'll just say the following. There's three mechanisms for what electricity is. Two of them belong to the religion of quantum mechanics. And one of them is, think of the wire in a circuit. And they say, well, how does electron flow? Well, first of all, they spiral. They can't explain that. They'll never be able to explain that because they would not know why the electron goes, in a spiral manner along the wire. That's the first one. But then there's another problem, and that's that, with a wire, they say, okay, the electron bead goes from atom to atom. It just goes to the outer shell and just continues from shell to shell. But when they're dealing with a slit experiment or with a vacuum chamber, they forget about the atoms. They get rid of all the atoms and they just shoot electron beads. That's what they think they're doing. They think they're just shooting electron beads, just a flow of beads from the source to the wall. There's no atoms there. They're not thinking of atoms because in the case of the circuit, they say, well, there's a wire, so let's assume it's iron. So you have all these electron beads going from iron to iron atom, from atom to atom. Boop, 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 boop. No problem. They can visualize that. They say, okay, yeah, there's the atoms there, and they're going from one atom to the other, knocking the other electron, and that one goes to the next one, that one goes to the next one, and knocks that one out, and so on down the line. Like, photoelectric effect. You have light hitting an electron, moving it. How light manages to pinpoint the electron is a different story because the electron is so small and doesn't have location. Turns out light always finds it and kicks it out. They never figure that out. They don't care about these things, qualitative stuff. Okay, but the question is when you evacuate a chamber, now you don't have any atoms because that's what evacuation means. That's what vacuum means, that you removed all the atoms. So now, if you have a cathode and an anode, you should be shooting electron beads. Just a bead, just a little tiny bead, bunch of them, gazillions of them, from one electrode to the other. The mean free path has to be much greater now because you removed all obstacles. There's no obstacle. You have perfect vacuum. 10 to the minus 100, 10 to the minus 1 millionth torr. So now the bead should flow easier. If you shoot a billion beads, none of them should recombine with anything because there's nothing there. All billion beads should go to, from one place to the other. They should all hit the anode in this case. And that's not the case. The case is that the more matter you remove from the chamber, you can't get an electric current flowing, which shows that electrons go from atom to atom. The correct one is the one with a wire. Electrons should go from atom to atom. You need atoms for the electron bead to flow and create current. And in the case of the rope model, we don't have electron flows. We don't have electron beads flowing. What we have is a drill bit twirling in place. All the atoms are connected, all the molecules, they're connected and they twirl. Now you can explain magnetic field because of the threads moving around. You can explain why the electron goes in a spiral along the wire. And you can explain, more importantly, you can explain voltage. Today they don't know what voltage is. They say there's a voltage drop. We'll call this one positive, we'll call that one negative. They could have said X and Y. They don't know what positive and negative means, or north and south. They don't know what these things mean. These are labels. Under the rope model, very easy. Clockwise, counterclockwise. That's something Mother Nature understands. She understands clockwise and counterclockwise because that's physics. You take a rope, like in my case here, okay, and that's clockwise. There we go. That's clockwise, okay. I hope that's clockwise to you. And that's counterclockwise, right? No, that's clockwise, sorry. That's clockwise, and this is counterclockwise, okay? So Mother Nature understands clockwise and counterclockwise, okay? She doesn't understand positive and negative. And I explained voltage about a month ago, but I'll go over that again next time. We're a little bit out of time, and I'll continue with this discussion on Wednesday. So stay tuned. We're not done with this yet. Again, this guy opened up a can of worms, Pandora's box, and we have evil all over science now, and I need to address these issues, okay? So I'll probably do a recap of what I talked about today and then move on to some of the other issues that were brought up or that came up, which are misconceptions, total misconceptions, by people like Peter, who is, as far as I know, a recent graduate, about a year ago or so. And all these people are coming out of college with the wrong ideas. And some of those ideas, or really all of them, have to do with this notion that there are particles out there, that they do everything with particles. That's the mediator, the invisible mediators for light, gravity, everything particles. Okay, so we'll see you on Wednesday. We'll see you next Wednesday, and I'll continue with this discussion. We'll see you then. Bye-bye.